I was just about to bring it up, like, my earbuds have microphone on them. Oh.
Okay. So we are in the middle of 3D joints, well, almost at the end of 3D joints. We talked about the weird one last time that introduced 4 variables. That was that was like a hinge joint or a pin joint without thrust. Remember what thrust means? It's going to be important in the next one.
Well, does it just mean that it's not constrained along that?
Along the axis. That's right. Yep. And so the next one is the same thing, but it does have thrust. So joint category 5. Oh, you already wrote this, I know, but remember, exam 1 is on Monday. And what did we say? So up through 2D rigid body static. So none of the 3D stuff that we're doing now is going to be on it, but there can be statics problems that are 2D. Okay.
So it won't have any of this 3D stuff on there?
Correct, none. Yep.
Are you allowing like any notes?
No notes, but I'll give you any equations. But in this class, there isn't much for equations either. Okay, so joint category 5. So this introduces 3 components of force. Two components of couple. And so it introduces 5 variables into Newton's laws. And there's only one of these. This is a pin or hinge joint with thrust. And that thrust is provided by some kind of flange on one or both side of the pin joint. So I will now try to draw that for you. So let's see. Yeah, that's not bad. Okay, and then the pin there. So this thing can rotate about its axis, and that's all it can do. It can't, remember the last one we did, that pin kept it from translating anywhere in that plane, but without the flanges on the side, it was free to translate along the pin, along the axis. Now that's restricted too. Okay, so that's where the 5th variable comes in. And so let's call this body 1, and then a free body diagram of body 1 would look like so we have a full vector of forces, and then so now we have two components of couple. Which of these two axes are going to have couples about them? So think of what rotations are restricted. I guess the easiest one is, we know there's only one axis that's not restricted, right? One axis of rotation that's not eliminated. Which one of those three is that? The one that it's free to rotate around.
The one on the left.
This one right here, yeah. That's the axis, and it's free to rotate around the axis. So the other two are gonna have couples. So I'll, so there's a component, a couple there. And a component here. And, you know, depending on, so let's call that MX and MY. So there's your 5. Yep.
So is the only difference between this and the double version of our previous example that it has no room to move back and forth along the rotating axis?
So so far this is just like the single version of the last one we did, and the only difference is that, yeah, there's that third force component along the axis because it can't slide along there. So remember if you look at the two compared to each other, this was the last one, and I kind of exaggerated that axis so that you could picture these two things sliding freely along that thing. Now those flanges on the side keep it locked from doing that. Okay. And this one, just like the other one, if you wanted to break a joint like this, the way you would try to do it is by applying those two couples, because these joints are not very good at applying those couples usually. And so you would grab it like this and pull it this way. That would work pretty well. And then if you could get a good lever arm, like put a like a lug nut wrench on the end of this and twist it that way, that would be a good way to break it too. Yep.
If it only had one of those limiting it in one direction,
Yeah.
it would just be like the last one, right? We treated it as a Python before.
If it only applied one of those couples,
Yeah.
yeah, we won't ever see anything like that. I'm not sure physically how it would happen, but yes, then, I mean, we wouldn't treat it just the same way, but it would introduce 4 variables into Newton's laws, that's right. Which 4 would be different? But anyway, so that thing isn't great at applying couples. And so usually in practice, this is used with another coaxial pin joint. And so like the pin joint without thrust, if this is part of a pair of coaxial pin joints, leave those couples out. And the reason for that is, well, this thing isn't very good at applying those couples. It's much better at applying forces. And if you have 2 of them on the same axis, the forces that they provide prevent those rotations. And so these joints don't have to provide those couples. Okay. And so usually we'll see it like that. We'll see a couple problems where it's just a single joint like this. But yeah. And then the last one, joint category 6. What's this one going to be? Yeah. So this is just the two bodies are fixed together. They have to move together. There's no motion between them. This introduces 6. Variables into Newton's laws. And so that would be like look something like that, where there's just totally fixed relationship between those two bodies. You could even think of them as a single body, and a free body diagram. I'll call this body 1. Would look like this. And then there would be couple components in all those directions too. Okay, so let's just do a couple of example problems and see how these work in actual problems. So for the first one, let's say there's like a big, you can think of it as like a sign. And it's being supported by a ball and socket joint over here. I got to give myself more room. And 2 cables. So one cable is at the end, and its location is okay, so that's a cable. And this distance is 2 meters. This distance is 1.5 meters. And then the second cable is 0.5 meter from the end. And it's connected to the wall 1 meter over and 1 meter up. And this distance is 0.5 meters. Are you with me on that? These get a little hard to draw, but both of these cables are connected to the same wall that that ball and socket joint is on. And this length is 2 meters. And this length is 1 meter. And we want to know, what are the cable tensions? And the reactions at the ball and socket joint. I guess I need to give a mass too, and the mass is 50 kilograms. Okay, so just like with 2D problems, I mean, you can just think of this as a lookup table thing. No matter what other joints are in the problem, this ball and socket joint, just go back, look up what loads it applies, and that's what you put in the free body diagram. But think about it for a second too, like think about the motions that are eliminated by a ball and socket joint. Okay, so if that ball and socket can't come apart, and that's what we're always going to assume, can this body translate away from the wall? No. Can it translate up or down, side to side? Okay, so we know there's a full vector of forces. And now think about rotations. Can it rotate about like this is a paddle? Can it rotate that way? Yeah, so there's no couple there. Can it rotate like a hatchet? Yeah, and then can it rotate flop side to side like a fish? Yeah, all those rotations are still allowed. And so this is only going to apply 3 components of force. Okay.
What was the mass?
50 kilograms. So we're going to start with a free body diagram. There's a weight force down. That's 490.5. There's a cable tension here. I'll call that T1. And then a cable tension here, I'll call T2. And then there's a vector of unknown forces here. I'll call that R. So based on that, the first thing you want to look at from your free body diagram is you can tell the number of variables that you have. And for a single rigid body, you know you only get 6 equations. So if you have more than 6 variables, the game is over, But this gives us 5 variables. With 3-dimensional problems, pretty often it'll come out that one or more of these equations are just going to come out to be trivial equations, 0 equals 0. That's what's going to happen here. So the fact that we have 5 instead of 6 isn't usually a problem, but you never know for sure until you see what the equations look like. Any questions about that free body diagram? Okay, so now in these 3D problems, this table is super, super helpful, okay? We have to choose an about point. It doesn't matter where, but I guess you might as well choose this. And here's the table, rho, force, moment, I'll do R first. What's the row vector for R?
0, 0.
Yep, and this is 3D, so you got to go 0, 0, 0. Now, because remember, in 2D, all of our moments just had a Z component. Now they're going to have all three components. It's going to be chaos. The force is Rx, Ry, Rz. And the moment is zeros. Now, the weight force. So the row vector is from the about point to where the force is applied. This whole thing is 2.5 meters long and 1 meter high. And so to get to the middle of this sign, we have to go 1.25 meters. Well, I didn't show what our coordinate system is, but let's use this.
Thickness still doesn't matter here?
That's right. Everything's happening down the center axis, so it wouldn't matter anyways.
It wouldn't matter as long as you use the same coordinate system for all of the math, right?
As long as they're all in the same plane, unless one of those cables was on one side and one was on the other side and that kind of thing. Okay, so here's the coordinate system I'm using. Okay, so we're going to go 1.25 meters in the positive x direction and then 0.5 meters in the negative y direction. The weight force is 0, negative 490.5, 0. And the cross product is 0, 0, negative 613.125. Okay, and now these cable forces. So the row vectors, let's come up with the row vectors first. I'll do T1 first. So that row vector is pretty simple. It just goes from the red dot to where that cable connects to the body. So that's just going to be 2.5, 0, 0. But now we have to think about this force vector, and that's going to be kind of a mess. How are we going to come up with an expression for this force vector? What we want is a unit vector in the direction of that force, and then we want to multiply it by T1.
The difference between its P and or the difference between where it is to where it ends up.
Yep, exactly. Yep. So to get that unit vector, we're going to take these coordinates minus these coordinates, and then we're going to normalize, divide them by the length, normalize them to get a unit vector, and then we'll multiply by t. Okay, so what are the coordinates of this point? So the coordinates here are 0, and then y is 1.5, and z is negative 2. And the coordinates at the connection point are 2.500. So I'm going to come down here, and my u, it's not a unit vector yet. I'll call it 1 to match with the T1. This is equal to 0, 1.5, negative 2, is that what it was? Mm-hmm. Yep. Minus 2.500. And so that's negative 2.5, positive 1.5, negative 2. How did I know which one to subtract from which one? Like, how did I know I wanted this minus this instead of this minus this?
Final minus initial.
Yeah, I mean, right. It's where that vector is pointing minus where the vector is coming from. And so it all has to do with the direction of that cable force. Okay, the cable force is always away from the chosen body, so that's how it came up that way.
If you chose to do it the other way, I mean, you would still get you would know in the end when your tension was negative, right? But
Yeah.
it would still work out, right?
Yeah, but yeah, if you
Or maybe not.
you don't want to do it that way because I mean you'd go through all those steps, you'd get a cable tension that was backwards, you'd suspect that's probably the problem, you'd find your problem, but you'd probably want to do the whole problem over again the right way, you know? And so you'd rather catch it at the beginning and have everything make sense just for confidence and stuff. Okay, so that's the vector. Now we want the unit vector. And
Have to come up with a negative tension from a different error.
yeah, you can, right. Okay, so this is, well, if you have a TI-89 or a TI Inspire, there is a function built in called unit V. And if you run unit V on that vector, it'll give you the unit vector in that direction, which is sort of helpful.
Unit V parenthesis.
Yeah, and then put in that vector. If you don't, that's an easy program to write, and that's all available on D2L. But anyways, what you get if you plug it into that program is negative 0.7071, 0.424, and negative 0.566. And you might wonder if it's important that I have 4 significant figures for my X component and 3 for my other 2 components. Yes, it's very important. And so finally, so there's our unit vector. And so that force vector is this times T1. So negative 0.7071 T1, 0.424 T1, negative 0.566 T1. And so that's our force. So over here, negative 0.7071 T1, 0.424 T1, negative 0.566 T1. Yep.
So that's certainly the easy way to do that. I've been checking my work by keeping my sine and cosine in there for the 2D stuff.
Yeah.
Is there a way to do that with 3D?
Not really. I mean, yes, there is, but this is the way you want to do it in 3D. Because you have to combine rotations out of plane and stuff. You could do it with rotation matrices, but you don't want to do that. So in 3D, you always want to find coordinates, subtract the coordinates, and then take the unit vector. Okay. Cosine and sine only work in 2D in any practical sense, you know. Okay. So now take the cross product of those, and you get 0 for x, 1.42 T1 for y, 1.06 T1 for z. And if up to this point in 2D problems, you've still been doing cross product by hand, and I have, it's pretty easy to do in 2D, but at this point you can kind of see, you just want to get comfortable doing this on your calculator for these 3D problems. And now we have the last one, T2, and we're going to follow pretty much the same steps. The row vector for this cable force T2 is 2, 0, 0. For that force, we want to get the coordinates of the connection point of this second cable. So that is going to be 0 for x, positive 1 for y, and positive 1 for z. And so our vector u2 is going to be 0, 1, 1, minus 2, 0, 0. So that's negative 2, 1, 1. Plug that into unit v to get the unit vector in that direction. And you get negative 0.816, positive 0.408, positive 0.408. And so the force vector F2 is negative 0.816 T1, positive 0.40, I wrote that wrong. This is T2 now. It's the other cable. T2. And positive 0.408 T2. So there's our second force vector. And so here we get negative 0.816 T2, 0.408 T2, 0.408 T2. Take the cross product of those two, and you get 0, negative 0.816 T2, positive 0.816 T2. Okay, so there's our complete table. And Newton's second law says we're going to add up all these vectors and they're going to be equal a 0 vector. And rotational Newton's second law says we're going to add up all these vectors and they're going to equal a 0 vector. And now you can look and you can usually see, like in this case, we only have 5 variables, right? So one of our equations needs to either be a linear multiple of the other 5, which we wouldn't be able to see by just looking at this, or it needs to be 0 equals 0. But you can see now, looking at these, that one of these equations goes away. There are things for the x component of the force. There are things for the y components of the force, things for the z component of the force. But the one that disappears is the x component of the moment equation. You see that? That's just going to come out to say 0 equals 0. And so we're going to get 5 equations for 5 variables, which is what we want. Okay, so let's, I'm going to draw out this matrix. We have, like I said, 5. Maybe I should write the, well, yeah, let me write the equations first before I do that. So Newton's second law says, I'll just put it in the vector form, Rx, Ry, Rz plus 0, negative 490.5, 0. Plus negative 0.7071 T1, 0.424 T1, negative 0.566 T1, plus negative 0.816 T2, positive 0.408 T2, positive 0.408 T2, is equal to 0, 0, 0. And then the moment equation says 0, 0, 0 plus 0, 0, negative 613.13 plus 0, 1.42 T1, 1.06 T1, plus 0, negative 0.816 T2, positive 0.816 T2 is equal to 0, 0, 0. And this X equation doesn't give us any information. So now we're going to have a matrix with 5 rows and 6 columns. One, two, three, four, five, six. So this is equation 1, 2, 3, 4, 5. And for variables, I'll go Rx, Ry, Rz, T1, T2, and then that's for the constants. The first equation, Rx's, we have 1. T1s, we have negative 0.7071. T2s, we have negative 0.816. Everything I leave blank is just 0. For the second equation, Ry's, we have 1. T1s, we have 0.424. T2s, we have 0.408. Constants, those have to be on their own side of the equation, so this is positive 490.5. For the third equation, RZs, we have 1. T1s, we have negative 0.566. T2s, we have 0.408. And no constants. For equation 4, T1s, we have 1.42. T2s, we have negative 0.816. No constants. And then for the last one, T1s, we have 1.06. T2, 0.816. Constant, positive 613.13. And that's it. Usually as these matrices get bigger, you get pretty sparse matrices like this without a lot of values and a lot of zeros. And then put this into reduced row echelon form, and you get that R is 525.9, 210.1, negative 35.6. Hold on. And this is all newtons. And then T1 is 247.2 newtons. And then T2 is 430.2 newtons. And then based on that, you can tell, what materials you need to use for those joints, what you have to attach, say that ball and socket joint to, what you can use for those cables. This is super important information when you're designing a, machine or system or whatever. Actually, this is funny. We had it's cool, really. We had a student here, it's a long time ago now, who he worked as a lab assistant for a while Jamie was on maternity leave, and he took this class, and then he did a summer internship working for an awning, like a company that makes awnings, and he was just doing these kind of calculations just for the whole summer to see like what they could support and stuff. And he works for MTS now. He's had a great career so far.
Where's MTS?
Mechanical Testing Systems. It's the coolest engineering company in Minnesota, I think. It started out as they just made machines that did mechanical testing of materials, which is something we'll talk about a lot in D-Form, not in this class, but basically just machines that so if you want to be able to do calculations for, say you have a certain alloy of steel that you've designed, and you want to do calculations based on how that's going to work in whatever setting, you have to do mechanical tests to determine how much it stretches for a given amount of force, how much when you stretch it out this way, how much it contracts this way. And with that, there's a surprising amount of information you can get from that. So they started out making machines that could very precisely, you could apply these forces and measure those distances and get these values. But then it turned into now like big companies will be like, we want to make a rover for like a Mars rover, or somebody wants to make like a piece of military equipment. And they're like, we need to know that it can support, driving at this speed over this kind of terrain, in this terrain. And so this company just it's all this one-off stuff where they'll just take this machine and figure out how they're going to measure what it can take. And, they'll build all this crazy equipment just to do testing for one company for one thing. It's a really cool company. And they're not far away. I mean, I know I've run into him in the Twin Cities, so I can't remember where it is, but one of the pretty nearby like suburbs. MTS, Mechanical Testing Systems. Okay, yeah. But yeah, look at their website. I mean, it's just a really cool place. The Twin Cities have some pretty awesome companies. I mean, all the medical companies and stuff, but that's definitely one of them.
One-off stuff is definitely the coolest.
Yeah, I know. Well, you just have to imagine how much money the company must be planning to make from this one thing in order to hire out another company to build equipment it's amazing.
So these would be like the theoretical minimum force you need to be able to handle?
Yes. And then usually with electrical engineering stuff, calculations are very, very precise. I mean, for statics, sure, this is precise enough. But when you get into mechanics of materials and like calculating deformations and stuff like that, really you're just kind of trying to get a kind of a ballpark figure. So when you do mechanical testing like this, you'll see what these are required. You'll say like, okay, we need cables that can support this amount of tension. And then you'll just throw in a factor of safety. We'll be like, make it twice that, what can it hurt? With electrical engineering, you never do that kind of stuff. But We have more fudge factors in mechanical engineering.
So would you say this is like the dead load on something then? And I've just seen that like in truss calculations where they have like two things where it's like a dead load and a live load.
Oh, I guess that would be for like bridges and stuff
Sure.
with
Yeah,
winds
like
and stuff.
structures.
Yeah, I guess I have heard that, but I don't really remember. But that's what I would imagine that means. Yeah, like
Well, in deform, do you get into problems with nickel titanium?
we really in deform we do not. Is that a shape memory material? Um,
Yeah, night.
We don't really get into specific materials much. I mean, we'll plug in values for steel and stuff, but no, not really. That you would see that kind of stuff, I guess, once you took material science, your first material science class. Yeah, but mechanics of materials and material science kind of go hand in hand. You know, I think at the university you take mechanics of materials, deform. And then after that, you take material science and it uses a lot of that deform stuff. Any other questions? So I guess Monday is the test, so we won't do anything on Monday. And then on Wednesday, we'll just do another problem like this before we go on to the new stuff.
Do you make hard tests?
I make them, yeah. Oh, hard? Oh. No, I make very easy tests, I guess you would have to say, and I have kind of a correspondingly like high grade cutoff, you know what I mean? I make tests that I'm just trying to see that you've done all the assignments and understood them, you know? If you feel good about the assignment problems, you'll look at the test and feel good about it.
Have we had a weekly assignment?
No, I'll give you one after, or I'll probably give one on Monday. Yeah.
I'm supposed to remind him.
Yeah. No, that's on my radar. I know. Okay, that's all.
No, I've been second guessing.